All right, thanks everyone, and thanks to the organizers for the opportunity to talk today about some work that myself and in collaboration with Tony Frawley at Florida State University have been doing on 4D track reconstruction at the SPHENIX experiment. So SPHENIX is a new detector that's being commissioned this year at the Relativistic Heavy Ion Collider, a proton-proton and primarily heavy ion collider at Brookhaven National Laboratory. And SPHENIX is a jet and heavy flavor probe detector. So we will make measurements in PP, P gold, and gold-gold collisions for direct comparisons to many of the measurements that have been made, many similar measurements that have been made at the LHC in the last 10 years. So we are reusing the Babar 1.4 Tesla solenoid. And a very exciting thing is that we're introducing hadronic calorimetry for the first time at RIC, so that we can make complete unbiased calorimetric jet measurements. So I just want to show a timeline here, since this community is more focused on the LHC, and just comment on where SPHENIX is. So SPHENIX was first proposed quite a long time ago now, seems like forever ago, in 2010 as a replacement to the SPHENIX detector at RIC. And since then, we have gone through a whole series of test beams and reviews and more than we can count. And we're now down here in 2022, where we are actually installing this detector. The pieces have been built, and it is actually being constructed at Brookhaven and put together, which is really exciting. So we have a 3-year run plan that's noted here at the bottom. We'll start taking data next year in February, where we'll take a gold data set that's primarily for commissioning and measuring some of the standard candles that we expect to measure, like upsilons and jets, for example. And then in 2024, we'll have this PP data set. RIC is also the world's only polarized hadronic collider, so we can measure transverse spin structure of protons as well. And then we will also have a short P gold data set at the end of the run. And then our sort of flagship data set is in 2025, where we'll have a high statistics gold run for something like 24 weeks. So SPHENIX has a unique set of run conditions because RIC will achieve the highest luminosities that it has ever achieved in its history in the next 3 years. RIC has been operating since 2000 actually, but these next few years are, the goal is really to complete the RIC scientific mission. And in these time periods, we will average something like 50 kilohertz gold data and 3 megahertz PP collisions. So this is quite high for RIC. And this translates to something like an average of 2 to 3 gold collisions or 20 PP pileup collisions measured in SPHENIX at any given time. So compared to the LHC, the PP data set is maybe moderate, but actually in gold, we expect hit occupancies of order hundreds of thousands, which are quite similar to those expected at the high luminosity LHC actually. So we will actually be tracking in very similar environments than in those that are to those that will be expected at the high luminosity LHC. Obviously, it's a little different because we don't have 200 vertices, for example, that we have to sort through, only a couple, but because of the occupancy of central gold collisions, we will have extremely high, a large number of hits. So of course, track reconstruction is very difficult in these pileup environments, as we all know. And just to give a pictorial view of this, this is an example event display of a 25 GeV B jet embedded in our 50 kilohertz gold background. And you can see by eye, there's no way you are picking out where that B jet is in this event. So this is both a challenge for the reconstruction as well as the analysis methods that we have to deploy to actually get physics out of SPHENIX. So SPHENIX is designed to be a high precision tracking and jet detector at RIC. We have a large hermetic acceptance, which covers the primarily central region of pseudorapidity -1 to 1. I mentioned we have hadronic calorimetry, which is a first at RIC, and we are going to collect a very large minimum bias data sample that translates to an offline data rate of something like 100 gigabits per second. This is a much more coming off the detector. This is what we're going to actually write to tape. So our primary tracking detectors are the MBTX, which is 3 layers of map staves. It's based very closely, almost identical actually, to the ITS technology that's used at ALICE. We then have an intermediate silicon tracker, or INTT, which is 4 layers of silicon strips. And then our primary workhorse detector is a compact gem-based TPC, which is this yellow guy right here in this engineering diagram. And this TPC is also very similar to the Alice TPC and its gem readout, but it's much, much smaller than the Alice TPC, something like a 30th of the total volume. So we don't actually get DEDX measurements from our TPC, but we do get excellent tracking resolution because of the large number of layers from the TPC. And then recently, we have added in the last 8 months or so, the TPC outer tracker, or the TPOT, which is 8 modules of micromegas that are going to be inserted between the TPC and the EMCal, primarily for the TPC calibration. So those can be seen here. It's a little difficult to see in this picture, but there are 2 modules kind of behind the TPC here. Then we have 4 that sit on a full Z section of the TPC, and then 2 others that are azimuthally offset. And just because pictures are fun and we're all very excited right now, this is a picture of our outer HCal actually installed around the Babar solenoid here. And this is in the experimental hall, so that's a very fun picture. And then this is our inner HCal, which is completely built now. And actually, these pictures are sort of old. Things are moving very quickly. Now the EMCal sectors are actually being installed inside of this, and then the whole thing is going to be slid into the solenoid. So it's a very exciting time. All right, so let me talk a little bit more about the tracking detectors. So the MDTX is 3 layers of map staves, and these give us precision space point identification primarily for the heavy flavor program. These pixels have of order 1 to 10 micron precision in R5 Z, and this detector has an integration time of order a couple microseconds, 4 or 5. And I point this out, I just want you to keep this in mind as we go through this. I intentionally laid this slide out to sort of highlight the differences between these detectors. The INTT is a silicon strip detector, which has order 10s of micron precision in R5, but this is a strip detector, so that we have nearly no precision in Z. But the INTT has a very fast order 100 nanosecond integration time, which is very intentionally selected because the RIC bunch structure is about 125 nanoseconds. So this is going to come into play throughout my talk. And then the TPC is 48 layers. I mentioned is a gem-based TPC, and depending on what layer, the TPC has order hundreds-ish of micron precision. However, the TPC suffers from a very long 13 microsecond drift time, and this creates a very this particular number here creates a very challenging environment for us to reconstruct tracks in. And then last but not least, the TPOT gives us an additional order 100 micron space point outside of the TPC, and is reasonably fast detector too, order integration time of order about a microsecond. So I laid this slide out intentionally to sort of highlight where each of these detectors comes in, and highlight that each detector plays a really critical role for our physics program. Without vertexing, we lose our heavy flavor program. Without timing, we're in major trouble because our TPC drift time is so long. Of course, the TPC is the primary tracking detector and gives us a handle on the curvature of the track since we have 48 layers. And then the TPOT is specifically for the calibration of the TPC. So it's really important that each of these detectors sort of interplays with one another for our tracking. So I liked the slide that Tom showed yesterday in the LHCb talk about where the RTA project was 2 years ago. So this is where our track reconstruction workflow was at the last Connecting the Dots workshop, and this is where we are now. So we have greatly expanded and made our tracking much more realistic. I'm not going to go through the details of this, but our track reconstruction workflow is significantly more complex now, and we have integrated the ACTS package throughout this workflow in a variety of places. So we are going to be really beta testing a lot of the features of ACTS next year when we take data as one of the sort of first experiments to implement a lot of these features into our reconstruction workflow. And for more information, you can see these 2 papers that have been published in the last year. So I want to highlight our sort of seeding, the seeding part of this diagram, and just show what our 4D tracking strategy is. We really try to reconstruct seeds in each detector individually, and then take the relevant pieces from the seed and create a full SPHENIX track seed at the very end, which we then go and do some fitting to. So this seeding diagram is sort of laid out in columns where we cluster in the TPC. The TPC is our most complicated detector, so we have a variety of things to do there. We cluster in the MVTX and INTT, and then do some track seeding there. And then the TPOT is just one measurement if the acceptance allows for it. And then at the very end, we sort of match all of these things together and take the momentum from the TPC seed, the vertex and timing information from the silicon seed, and then some calibration information if it's available from the TPOT measurement, depending on the acceptance. Okay, so just to show how this actually works, in the MVTX and INTT, we start with the ACTS seeding algorithm in our MVTX, and this was discussed a little bit yesterday, and then we propagate that track seed out to the INTT to find any additional measurements that may match the track. So this is what our efficiency looks like for this algorithm in our realistic gold 50 kilohertz background sort of environments. So we do quite a good job, and I would note that 3 to 4% of this efficiency loss is from tracks that only leave 2 measurements in the MVTX. So we literally can't find them, and we're working on an iterative tracking strategy where we go back and try to recover these tracks in a later iteration. Our TPC seeder is a cellular automated seeding algorithm that was actually developed by Alice and is being used, deployed in GPUs in Run 3 for them. We have used this on CPUs actually. But the Alice, this algorithm chains links of triplets together and is very efficient and computationally fast. And that was primarily the reason that we moved to this, because we will be reconstructing our data on a very limited set of computational resources. So it's extremely important that our track reconstruction is fast. Right now, we average about something like 10 to 15 seconds per gold event, which is several orders of magnitude lower than what it was a few years ago. So we've come quite a long way in terms of improving the code. So then we take those tracks, match them together, and then fit them with the ACTS track fitter. And again, as I mentioned, our common filter rather from the ACTS package. And as I mentioned, our track seed kind of takes each of the important parts of the seeds and builds a complete SPHENIX seed from them. So this is what our efficiency and PT resolution look like right now in both the PP and gold environments that we expect to take data with. Okay, so I want to talk a little bit more about the timing information in these track seeds and how relevant and important it is. And I think this sort of dummy example really highlights this. This is a plot of the number of reconstructed tracks as a function of their truth time of origin in our simulation for 3 megahertz minimum bias PP collisions. And you can see if for these tracks, we only require that they have some TPC measurements, and you get a huge number of out-of-time pileup tracks. And this is again because of this long 13 microsecond drift time that the TPC suffers from. If you zoom in on this plot, this is the same plot just zoomed in, you'll actually notice that these tracks are spaced exactly 125 nanoseconds apart, which is exactly the RIC bunch structure. So this again motivates why we need this fast silicon strip detector to identify the tracks from these bunch crossings. And actually, if you just look at TPC tracks, we actually reconstruct tracks from nearly every bunch in the RIC ring. So this is a huge amount of pileup that we have to deal with. If you just require that the track has some MVTX measurements as well, then you reduce this out-of-time pileup significantly. And then if you take another step and request that the track has an INTT measurement, you greatly suppress the number of out-of-time pileup tracks that we reconstruct. And note, this is not actually explicitly including the timing in our reconstruction, which I'll talk about in a little bit. This is just requiring that the track has an INTT measurement. So this is a huge suppression of out-of-time pileup. So our tracking environment is further complicated by the fact that we're going to be streaming 10% of our PP data, much like LHCb and Alice do. It's very similar in that way. They are streaming a much larger portion. We stream an additional 7 microseconds after some hardware trigger. So this diagram kind of pictorially shows this. This red line is a hardware trigger like an EMCAL cluster or something like this. And then we stream the additional 7 microseconds of data out, which corresponds to about 67 bunch crossings. And we do this for each of the 3 tracking, primary tracking detectors. And this is going to increase our hard to trigger PP data sample, like for example, low PT heavy flavor decays, much like we heard about from LHCb by many orders of magnitude. This further is complicated by the fact that our TPC has distortion corrections that we have to deal with. So in an ideal TPC, primary electrons drift longitudinally at a constant velocity. So in this picture, track liberates some charge, and this charge would, in principle, drift at exactly the same X and Y location to the readout plane, where you can then infer the Z position from the drift time. And of course, life is hardly ever ideal. So we have several sources of distortions from this that we have to consider. So there are static distortions that are order centimeters that change on the order of timescale months. There are beam-induced distortions that are really luminosity, that are from luminosity, that are order millimeters and change on the timescale of order half an hour or so. And then there are event-by-event fluctuations that are due to local multiplicities in an event that are order 100 micron and change on the order of milliseconds. So you can really think of these as sort of a unique type of alignment problem that a TPC has to deal with. And of course, these large distortions here, centimeter and millimeter, really impact our physics program if we do not correct them. Our TPC resolution position resolution needs to be something like order 100 microns. So we need to take into account these distortions when we do streaming readout. As a reminder, when we stream our data, we're reconstructing tracks that are produced up to 7 microseconds after the trigger. So this corresponds to about 67 bunch crossings. However, we have to do our TPC seeding without any distortion corrections because we don't have an explicit hardware trigger. So we do not know where the TPC clusters are in Z at all. Remember, what we measure is the drift time, not the Z position. So since we don't have a T0, we have no way of knowing where in Z those clusters are. However, we cannot match the TPC tracks to the silicon tracks without reasonably precise beamline seed track parameters. If you don't know the eta of the track, for example, you have a hard time matching it to the silicon. So we have kind of a chicken and an egg problem where we need to have distortion corrections to match tracks, but we need to match the tracks to be able to do the distortion corrections. So what we actually have to do is we move the clusters sort of arbitrarily in the TPC so that the tracks point to Z equals 0. We make some very approximate static distortion corrections and then move those clusters back by the same amount so that we can do the track matching. And what is going to happen is that we're going to have to sort of make iterative corrections to these distortions and iteratively improve them as we learn more and more about the actual space charge distortion in the TPC. So after we sort of artificially move these TPC tracks to make some initial corrections, we can then determine precise enough beamline track parameters where we do the silicon to TPC track matching. And we do this in eta phi x and 0, or a D0 as a lot of the LHC experiments use. And then from this, we get the crossing number as identified by the INTT clusters and can correct the TPC measurements for this crossing time offset, and then check that the silicon and TPC tracks actually match in their Z position. Assuming they do, then we treat that as a real track and actually try and fit it with the Kalman filter. And if they don't, then we know we have an out-of-time pileup measurement and we discard the seed. So just to show how this is performing right now, this is a plot of our efficiency and our DCA in the XY plane resolution as a function of PT in 3 megahertz PP minimum bias collisions, where you stream the additional 7 microseconds of data. I'll note that there are no uncertainties on this plot. These uncertainties become quite large after 3 GeV because these are minimum bias PP collisions. So there's no real hard type of event. The DCA here is predominantly limited by the vertex reconstruction because, again, these are minimum bias collisions. So there's something like 4 tracks per event at our center of mass energies of 200 GeV at RIC. But nominally, we achieved quite good performance. Another set of plots that I think really highlights how important the timing information is that the number of reconstructed vertices for all tracks in our streaming readout mode is 30 times larger than at crossing 0. So if you look at this plot, this is the number of tracks per vertex. And you can see, again, this peaks at something like 2 or 3 tracks for all of the bunch crossings. And this histogram has something like 60,000 entries. And if you only look at the nominal bunch crossing that occurred in our sort of nominal interaction region, this drops to something like 2,000 vertices. So we have a tremendous amount of out-of-time pileup that we have to measure and account for in our track reconstruction. so that we are not inadvertently including wrong tracks into our analysis. Okay, so I'd like to finish up by just making a comment about the electron-ion collider. Coming from the more nuclear physics community rather than HEP community, the EIC is the next generation precision QCD facility that was just approved CD1 in the DOE funding route. So this is actively going ahead with construction and design. And the EIC will have extremely unique tracking challenges with both its planned streaming readout. So we intend to stream 100% of the data, again, much like LHCb and EIC, and also its high luminosity environment. This machine will have luminosities of several orders of magnitude larger than Hera, which was the previous electron proton collider. So we will have extremely challenging environments to track within again. And we just went through, or the community just went through a proposal effort in which 3 detector proposals were vying for the sort of project detector. And I don't want to get into the details of those proposals, but what I do want to mention is that all of the proposals included a layer of AC LGAD detector technology to provide precise timing information and an additional tracking space point. And all of the proposals included a streaming readout DAC to collect complete unbiased data samples. So 4D tracking is going to be essential for achieving any sort of physics that we want to do at the EIC, at RIC, with SPHENIX, as well as obviously the high luminosity LHC. So I think there's a lot of synergies and interesting ways that we can collaborate between the nuclear physics and high energy physics communities on a lot of these problems. And a lot of this is already starting to happen with, for example, the HEP Software Foundation, as there's more nuclear physics involvement that's starting to get involved in the HSF. Okay, so to conclude, SPHENIX is going to be a precision QCD jet and heavy flavor experiment. And this, of course, requires that we have robust track reconstruction in our high occupancy environments that we will take data in. And our tracking detectors were uniquely selected and complement each other to provide important pieces for 4D track reconstruction, both in our triggered mode and in our streaming readout mode. So both of these environments are going to create complex reconstruction in which really 4D reconstruction is a necessity. We have to include the timing information if we want to get any sort of handle on our TPC because of this long drift time. And future facilities like the high luminosity LHC and EIC are already planning for 4D tracking, and there's a lot of continued progress being made in this sort of tracking research area. So I think there's a lot of opportunities for collaboration as we move forward towards these facilities. So thank you.
Okay, so questions in the room. Or questions on Zoom or also low.
There's one.
Oh, okay. Please go ahead.
Yes, hi. Thanks for the nice talk. I was just wondering if timing information is also used at the clustering level, or it's just for track building.
Yeah, so it's used at the clustering level. So the INTT clusters are what actually contain the timing information. And then we explicitly use that in the track seeding and track building phase when we are trying to match the TPC tracks to the silicon tracks. Another area that we plan to sort of improve upon this on is the MVTX is kind of a unique detector in that it has a strobe window in which the data is actually read out. So we don't actually, because of this, the MVTX detector has a 5 microsecond integration time. We can't identify the bunch crossing from it alone, but we can identify a window of bunch crossings to which it might belong. So in our silicon seeding, we plan to implement a timing sort of check that any INTT clusters that really have the precise timing information fall within the same MVTX strobe window that the INTT cluster actually belongs to, if that makes sense. And this should help reduce our out-of-time pileup even more in the silicon, which comes from the MVTX having a longer integration time.
Now I got a bit confused. When you said timing on the Okay, on the SPHENIX detector, this is not airguards with a picosecond resolution, like you are saying here that 4D points. So this is just for the time cross, for the crossing or whatever, for the clock. You have enough resolution to distinguish the different bunch crosses.
Yes. So
It is not precise timing.
yes, right. So the INTT does not have picosecond timing resolution, but we don't need it to because we only need it to be able to differentiate between the rig bunch crossings, which are 125 nanoseconds spaced apart. So at the EIC, that will not be the case. The bunches will be much more tightly, it will be much more high luminosity machine than even rig in terms of just raw luminosity. So that is why at the EIC, we will need really 10 picosecond timing resolution.
Any more questions in the room? One in the back?
What is the difference in the efficiency curve shown on slides 9 and 11?
I can't actually see the slide because it's the Zoom thing's annoying. 9 and 11. Oh, so this is just the efficiency of us finding a silicon seed that corresponds to a truth track. And this efficiency down here is actually our total track reconstruction efficiency. So this is the efficiency that we would deliver to users to do whatever physics analysis they want to do. And this is something that we are trying to work on improving too. I think so a comparable experiment would be Alice for us in terms of the tracking. And I think they achieve something like 80–85% for fully matched tracks that include their silicon and TPC. So we have a couple sort of aces up our sleeve that we hope to improve this a little bit more. But it probably will not improve, another 15% from this because the high occupancies that we deal with are just very difficult to track in.
Okay. Another question?
Can you? Okay, well, you were mentioning about these distortions on the TPC. So I was just okay. I was curious to understand what this problem is really the pileup, which is driving the.
So what happens is that a track traverses the TPC and it liberates some charge, right? So what happens is this creates a sort of pancake of positive ions that flow towards the central membrane. And that means you have a huge amount of charge suddenly that's moving through the TPC that is distorting the actual fields for other tracks that you're reconstructing. So it's an inherent problem of a TPC that becomes much worse at high luminosities because you have more and more tracks traversing it, so you have more charge liberated, and you have more of these pancakes that distort the fields. If that makes sense.
Oh yeah, okay, but then it's really let's say an occupancy problem more than a distortion or whatever.
Some of it is. These last two are really occupancy related. The first one is simply a result of you have this is embedded in some magnetic field, right? And when you're liberating that charge, you're creating an inhomogeneous electric field that then distorts things on this very large scale.
You have a current. And
yes. But you're right that these two are really primarily luminosity or occupancy based. This one happens no matter what, which is why it's on the order time scale of order months. To correct for these, we really we have a laser system that will just illuminate the TPC with some known truth charge, and then we can actually measure at the end without any beam effects or whatever where that charge ends up.
Oh, so that was actually my question. So can you describe that one more time? So
Yeah.
So how do you, because obviously there's a huge number of various distortions that can make this very difficult. So what do you use to ensure that one, you're doing it correctly, and two, the symptom that you're doing it correctly, because the heavy ion or lead or gold is a very occupied environment.
Yeah, this is our biggest challenge by far. We've spent years working on this problem and are not even, we'll turn the detector on and It probably won't even be like, what we expect. But the static distortions I just mentioned, we have a laser system that will pulse at some frequency that illuminates some charge on the central membrane that will drift, and then we can actually, without any beam effects, we can tell. These beam-induced distortions we will actually measure with data with tracks. So that's what the teapot detector is for. We can get precise space point measurements with the silicon inside the TPC, and then we'll have an additional precise space point outside. So we can fit that track and then basically identify the residuals in the TPC and determine distortions that way. And then this last one is also going to be corrected by a pulse laser that will pulse at the same frequency that we take data at 15 kilohertz, so that we can actually measure very time constrained distortion effects.
And then will you be checking the, I don't know, various physics objects using proton-proton for calibration purposes, or is that not?
So we'll have to do it for both gold and proton-proton data, because the proton-proton data, we also have the streaming readout DAC. So that presents additional challenges because we don't have a trigger in those bunch crossings to sort of nail down where the clusters are in the TPC. So it's a similar problem in both cases, but not exactly transferable. There are challenges in each, if that makes sense.
Okay, thank you. Any other questions? Okay, if not, let's thank you.